The internet glance is so far away that it's catching light that has been traveling for more than 13 billion years. The universe has been expanding, and thus, since then, the light has been spreading. The majority of distant worlds we recall are close to the time of the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from our reference to the singularity. Currently, this operates in a manner that could apply to the Big Bang Theory's interpretation. Nevertheless, the James Webb Space Telescope, JWST, has shed light on important mysteries about the birth and development of the universe, mysteries that leave us speechless. The renowned physicist Brian Cox has declared that the significant discoveries made by the JWST might actually alter our perception of the universe as a whole. Join us as we delve into these brand new discoveries about the heavens that promise to alter our understanding. The Space Telescope, named after the well-known NASA administrator James E. Webb, remains a wonder in the currently underway galactic investigation. This telescope represents a huge mechanical advance from its predecessor, the Hubble Space Telescope. It came about as a result of collaboration between the American Space Agency NASA and the Canadian Space Agency. The JWST surpasses the capabilities of its predecessor by employing cutting-edge technology and a design enhanced for concentrating on the universe in remarkable detail. Like the Hubble, the JWST conveys sharp pictures of far-off heavenly bodies. However, it primarily operates in the fascinating infrared range. This component permits it to penetrate astronomical relics and capture divine objects that were previously hidden from our view. With its massive 6.5-meter principal mirror, constructed from 18 hexagonal sections, the JWST dwarfs the Hubble's reflector. Located approximately 1.5 million kilometers from Earth at the second Lagrange point, L2, it orbits in harmony with the Sun and Earth, ensuring a steady and continuous view of the universe. From this vantage point, it explores the edges of the universe. But it also involves a kind of time travel. The JWST uses instruments that detect in the infrared to observe things and events from the cosmos dating back billions of years. Due to the expanding universe, the light from these objects moves through a redshift, shifting from the visible range to the infrared frequency. Luckily, the JWST can recognize this infrared light from heavenly bodies at extreme distances, enabling researchers to investigate stars, study galaxy development, and examine exoplanet atmospheres. Its most recent historical discovery involves identifying an incomprehensible mass of cosmic systems at the edge of the observable universe. This finding casts doubt on the veracity of the current theory of how things came to be, provoking a reassessment of our core cosmological assumptions and helping us understand how we arrived at this point. Let's go on a brief excursion through the history of space exploration. Civilizations like the Greeks and Chinese laid the foundation for understanding planetary movement by observing celestial bodies. In the 17th century, Newton's laws provided a conceptual framework for space travel. In the mid-20th century, Edwin Hubble, an influential and historic astronomer, revolutionized cosmology with his observational approach. He discovered that distant nebulae were, in fact, galaxies beyond the Milky Way. Hubble's law showed that galaxies farther away are moving away at higher speeds, providing solid evidence for the expansion of the universe. The post-World War II era marked the beginning of the space race. In 1957, the Soviet Union launched Sputnik, the first artificial satellite in orbit. This was followed by Yuri Gagarin's orbital trip in 1961 and the Apollo 11 moonwalk in 1969, all crucial accomplishments in human space exploration. Fast forward to 1990, when the Hubble Space Telescope was launched. It offered exceptional clarity and stunning insights into the universe. The journey from early observations to the James Webb's technological marvel showcases humanity's constant improvement in interpreting the cosmos. Hubble uncovered the vast expanse and transformation of space. One of its most iconic achievements was capturing the pillars of creation in the Eagle Nebula, revealing a star nursery formed by massive columns of gas and dust. Another significant accomplishment was the Hubble Deep Field Image, which captured a vast number of galaxies in what appeared to be a void patch of space. The HST also analyzed the atmospheres of exoplanets, identifying components like water and organic molecules in distant worlds, hinting at the possibility of habitable zones beyond our solar system. It also provided insights into the life cycle of massive stars, such as supernova SN 1987A. These successes established Hubble's legacy as the foundation of modern cosmology. The James Webb Space Telescope was launched to advance this legacy, utilizing the latest technology to represent our evolving understanding of the universe's origins. According to the prevailing theory, the universe began approximately 13.8 billion years ago as a hot, dense singularity. It rapidly expanded, giving rise to matter, energy, and fundamental forces. As it cooled, atoms, stars, galaxies, and cosmic structures formed. The Big Bang theory also explains cosmic microwave background radiation and the abundance of elements observed today. Despite being widely accepted, the Big Bang theory initially faced doubt and competing models, like the steady-state theory, which proposed a universe without a beginning. However, the discovery of the cosmic microwave background radiation in 1965 provided crucial evidence supporting the Big Bang model. Later missions like COBE and WMAP, alongside technological advancements, reinforced it with precise measurements. Enter the James Webb Space Telescope, equipped with advanced infrared instruments capable of peering through cosmic dust. It captures light from the universe's earliest moments and observes the formation of stars and galaxies shortly after the Big Bang. Its infrared capabilities allow it to see regions that are invisible to the eye, celestial nurseries and the birthplaces of stars. It focuses on light in the longer infrared spectrum, which can pass through stellar dust, overcoming one of Hubble's key limitations. The JWST can observe cooler objects like brown dwarfs and distant exoplanets. As celestial bodies move away, the light waves they emit are stretched, a redshift, shifting into longer wavelengths. The JWST can detect these redshifted signals, capturing light from the early universe and offering insights into its development. Intense events, such as black hole mergers or newborn stars, primarily emit in the infrared. The JWST's sensitivity allows it to explore phenomena that would otherwise be obscured or unnoticeable by optical telescopes. Recently, it revealed something astonishing: vast galaxies at the outermost edges of the observable universe. These ancient galaxies existed just a few 100 million years after the Big Bang. The baffling aspect of this cosmic dawn is that we are still unsure how such structures formed so quickly. This surprising discovery has left scientists re-evaluating long-held beliefs about the early universe. The existence of such massive galaxies at such an early cosmic time contradicts current models of galaxy formation. According to our best theories, there simply shouldn't have been enough time for such large structures to form, and yet, the JWST sees them clearly. This means we may need to revise our understanding of how galaxies evolve, how matter clumps together under gravity, and how quickly the first stars and galaxies were able to form. It's possible that the physics of the early universe was more complex than we imagined, or that some unknown process accelerated galaxy formation. These early galaxies are not only massive, they're also surprisingly well organized. Some show evidence of disk-like structures, suggesting that they had already developed into mature systems, not the chaotic, irregular forms that astronomers expected to see from this time period. This maturity in the youth of the universe is what has shocked the scientific community. Furthermore, the JWST's ability to detect the chemical fingerprints of these ancient galaxies, including the presence of heavy elements like oxygen and carbon, suggests that generations of stars had already lived and died within them. This points to an even earlier wave of star formation, further back in time than we ever thought possible. One of the telescope's major goals is to peer into the so-called cosmic dark ages, the time after the Big Bang but before the first stars lit up the universe. With its powerful infrared vision, the JWST is beginning to pierce through this veil, capturing the light from the first luminous objects. Another breakthrough is its ability to study exoplanet atmospheres in unprecedented detail. By analyzing the starlight that filters through an exoplanet's atmosphere during a transit, the telescope can detect the presence of gases like water vapor, methane, carbon dioxide, and more. These atmospheric signatures give us critical clues about a planet's habitability, or even the possibility of life. For instance, the JWST recently analyzed the atmosphere of a planet known as K2-18b, a super-Earth located about 120 light-years away. It found possible traces of dimethyl sulfide, a molecule that, on Earth, is only produced by living organisms. While it's far too early to claim life beyond our planet, these findings are pushing us closer to answering one of humanity's biggest questions: are we alone? Beyond exoplanets, the telescope is also observing the birthplaces of stars in rich detail. Massive stellar nurseries where clouds of gas and dust are collapsing under gravity to ignite new suns. Structures like the Carina Nebula or the Orion Nebula, when viewed through the JWST, reveal intricacies hidden from every previous telescope. These findings aren't just about filling in gaps in our knowledge, they are redefining the entire timeline of cosmic history. With every image and every dataset, the JWST is transforming our understanding of the universe's structure, origin, and evolution. And perhaps the most thrilling part is this: we are only at the beginning of the JWST's journey. Its mission is expected to last more than a decade, and as it continues to observe, it will likely uncover more surprises, discoveries that challenge the very foundation of physics, astronomy, and our place in the cosmos. Early on, enormous structures formed. This discovery in the universe's history might cause us to re-evaluate our understanding of the formation and development of galaxies. Observing early galaxies is crucial for unraveling the mysteries of cosmic origins. The JWST can gain insights into how stars and galaxies, and over time, planetary systems, developed and changed. These observations span billions of years and also contribute to more general inquiries regarding the fundamental character of the universe, including its elements, structure, and the factors that control its evolution. While the Hubble Space Telescope was revolutionary, it was limited in its ability to observe the early universe. Its main limitation was its inability to effectively penetrate cosmic dust and detect infrared light from galaxies that once existed. Hubble was based on visible and ultraviolet light observations, which made it challenging to explore the early universe, where these wavelengths are absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope signifies an important leap forward in observing galaxies from the universe's initial stages. The JWST, in contrast to its predecessors, can observe the formation of celestial objects within the first few 100 million years after the Big Bang. Using its infrared sensitivity and advanced imaging capabilities, the JWST has uncovered an abundance of ancient galaxies, offering remarkable detail and clarity in our comprehension of the universe's evolutionary history. Preliminary results from these early observations have sent ripples through well-established models of the universe. The detailed data challenges several aspects of current theories, causing cosmologists to reconsider fundamental guiding principles regarding cosmic evolution and structure. Differences between observed data and theoretical predictions have sparked intense debates in the scientific community. Observations have revealed a larger number of galaxies in the early universe than anticipated. Current models suggest a more gradual and less complex evolution, yet some observed early galaxies appear to be more developed and evolved more quickly than expected. The discovery of an unfathomable mass of galaxies challenges the assumed distribution and arrangement of massive structures. These findings suggest a more complex and denser cosmic web than previously believed. They raise fascinating questions and avenues for further exploration. The existence of such large structures challenges early models of cosmic formation, prompting researchers to refine models and improve our understanding. How these vast structures grew so quickly after the Big Bang remains a puzzle. It requires an explanation that doesn't violate fundamental cosmological concepts. There may have been substantial differences in the early universe compared to what our current models predict. These variations may suggest previously unknown physical processes, unexpected conditions, or unidentified cosmic phenomena. In simple terms, scientists are now rethinking and improving our models of the universe. All we can say for certain is that further exploration is required to incorporate these surprising observations into a more comprehensive understanding. Observations often provide exciting glimpses into the universe, but in-depth investigations sometimes reveal discrepancies. For example, early observations might show specific arrangements or properties within distant galaxies that, upon closer investigation, reveal alterations in composition, structure, or evolutionary paths. These enormous phenomena are extremely intricate and require careful investigation to truly comprehend their nature. Spectroscopy, a method used to unravel the properties and history of celestial objects, is one illustration of this process. By analyzing the light emitted or absorbed by astronomical objects, spectroscopy provides detailed information about their chemical composition, temperature, density, and motion. This analysis helps us understand the origins, development, and contributions of these objects to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations were corrected by later investigations. For instance, first observations of faraway galaxies suggested simple structures dominated by light elements like hydrogen and helium, which aligned with theoretical expectations. However, spectroscopic analysis using the JWST revealed fascinating differences in elemental signatures, identifying heavier elements or compounds previously undetected or misunderstood. This defies conventional ideas about the mechanisms and chemical compositions responsible for early development and distribution across vast distances. Initial assumptions about galaxies in the early universe suggested a fairly regular pattern of development and organization. However, in-depth examinations by the JWST revealed a much more diverse and complex array of chemical compositions within these galaxies. The James Webb Space Telescope continues to redefine our understanding of the cosmos by illuminating previously hidden corners of the universe. One of its most exciting capabilities is its capacity for exoplanet research. By analyzing the atmospheres of planets orbiting distant stars, the JWST can detect crucial chemical signatures, such as carbon dioxide, water, and organic compounds like methane. These findings offer valuable perspectives on the potential for habitable exoplanets and the conditions that might support life beyond Earth. In addition to exploring distant worlds, the JWST is transforming our understanding of star formation. It can observe the birth of stars in regions surrounded by dense clouds of gas and dust, regions that optical telescopes cannot penetrate. With its ability to detect infrared light, the JWST captures the faintest glimmers of new stars as they emerge, offering a clearer picture of the processes that lead to star and planetary system formation. By studying these regions, astronomers are gaining a deeper understanding of how stars like our Sun come into existence and evolve over time. Another outstanding feature of the JWST is its ability to peer into black holes at the centers of galaxies, particularly supermassive black holes believed to reside at the heart of most large galaxies. With advanced instruments, scientists observe how matter behaves around black holes, providing new insights into their growth, influence on galactic evolution, and the powerful jets of energy they emit. These findings help astronomers assemble the story of how galaxies and their central black holes evolve together, influencing each other's growth. Moreover, the JWST's discoveries are not only providing answers to long-standing questions but are also raising new ones. As it probes deeper into the universe's past, it continues to reveal phenomena that challenge existing theories and models. These difficulties drive the scientific community to refine current models and open new avenues for research. The discoveries of the JWST are not merely pushing the boundaries of what we know, they are helping reshape the very principles by which we understand the universe itself.